Let's jump right in. Today, we are exploring the fascinating, incredibly layered mystery of the microscopic universe. In this explainer, we're taking a deep dive into the structure of atom, guided by the foundational concepts compiled by Ridham Singh. You know, for the longest time, humanity thought of the atom as the ultimate indivisible building block of reality, just a solid, unbreakable sphere. But as we're about to see, the truth is way more complex, a whole lot weirder, and honestly, infinitely more beautiful. Here is our roadmap for today. We'll hit unlocking the subatomic world, evolution of atomic models, light, energy, and waves, the quantum revolution, and finally, deeper into the nucleus. Before we get into the heavy science, let's anchor ourselves with this quote from the source material. It says, "The rich diversity of chemical behavior of different elements can be traced to the differences in the internal structure of atoms." This really hits the nail on the head as to why all this matters. The fact that gold is shiny, that sodium explodes in water, that carbon forms the basis of life, it all comes down to the microscopic architecture we're about to unpack. Section 1. Unlocking the subatomic world. Let's meet the fundamental cast of characters that shattered that old idea of the unbreakable atom. Once scientists realized atoms could actually be broken apart, they found three crucial subatomic players. Check out this table. The big takeaway here is how the negatively charged electron is virtually massless compared to the heavier, oppositely charged proton and the neutral neutron. You can see its mass is essentially listed as 0. It is incredibly light. The proton and neutron are doing all the heavy lifting in the mass department. Section 2. Evolution of atomic models. So we have our particles, but how are they actually arranged? Well, it wasn't a straight line to the truth. It was a rapid-fire decade of discovery from 1904 to 1913, where each new model basically patched the fatal bugs of the previous version. J.J. Thomson had just discovered the electron, right? But he knew the atom overall was neutral. So he initially pitched what we call the watermelon or plum pudding model. He assumed the positive charge and mass were just a big, evenly spread out, uniform soup, with those tiny negative electrons stuck inside it like watermelon seeds. It made total sense at the time, but it really wouldn't last long. Enter Ernest Rutherford. He fired high-energy alpha particles at a microscopic sheet of gold. If Thomson's watermelon model was right, those particles should have punched right through that soft pudding. But they didn't. His famous gold foil experiment proved Thomson completely wrong because some particles actually bounced straight back. Rutherford realized the atom is mostly empty space with an incredibly dense, positively charged core at the center and electrons orbiting around it like a miniature solar system. But hold on, Rutherford's model had a glaring issue. If you have a negative electron orbiting a positive nucleus, why doesn't electrostatic attraction just pull it in and destroy the atom? Classical physics dictates that an orbiting charged particle should emit radiation, lose energy, and spiral right into the nucleus in a fraction of a second. But atoms are stable. You are made of atoms and you aren't currently collapsing into a subatomic black hole. So what were they missing? Section 3. Light, energy, and waves. To solve the collapsing atom problem, Niels Bohr actually had to look at how atoms interact with light, specifically the photoelectric effect. This reveals that light isn't just a continuous wave. When light hits a metal surface, it knocks electrons loose, but only if the light is of a certain frequency. Turning up the brightness of a low-frequency light doesn't do a single thing. This proved that energy comes in distinct, specific chunks, or quanta. This was a massive breakthrough. Light has a dual nature. It behaves like a continuous wave sometimes and like tiny particle packets of energy at other times. This, combined with the barcode-like light spectra that different atoms emit, gave Bohr exactly the tools he needed. He proposed that electrons can't just orbit anywhere. They have to stay in very specific, fixed, quantized lanes. Instead of getting bogged down in the algebra here, just look at how beautifully Bohr's formulas work. They let us calculate the exact energy and radius of an electron's fixed orbit. Looking at the first orbit of a helium ion, Bohr proved mathematically that electrons have a ground state, a lowest possible energy level. They literally cannot spiral into the nucleus because there simply isn't an energy state available closer than that very first orbit. Quantum rules saved the atom. Section 4. The quantum revolution. But of course, Bohr's neat circular planetary orbits weren't the final answer either. As our tools got sharper, the universe got blurrier. Because electrons also behave like waves, Bohr's fixed, precise paths are physically impossible to track. This is the Heisenberg uncertainty principle. It tells us that the more precisely we know where an electron is, the less we know about how fast it's moving. We can't draw a neat circle anymore. We can only talk about the probability of finding an electron in a 3D cloud, which we call an orbital. To map out this probability and understand how elements actually behave, nature follows 3 strict rules. First, the Aufbau principle. Electrons are basically lazy. They fill the lowest energy seats first. Second, the Pauli exclusion principle. Think of an orbital as a 2-seater couch where the electrons must have opposite spins. Finally, Hund's rule. Electrons don't like to share if they don't have to. They will singly occupy all the empty seats in a subshell before pairing up. These 3 rules dictate the entire periodic table. Section 5, deeper into the nucleus. For our final stop, let's zoom past the complex electron clouds and dive straight back into the dense core. We used to think protons and neutrons were the end of the line. But guess what? They are actually built from even smaller, slightly differently weighted particles called quarks, specifically up and down quarks. A proton is 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. Because down quarks are just a tiny bit heavier than up quarks, this perfectly explains why the neutron is slightly heavier than the proton. It's like a giant, beautiful puzzle. So, we went from a solid, indivisible sphere to a watermelon, to a solar system, to a cloud of probability, and down into the quarks themselves. The journey inward never seems to stop, does it? It really leaves us to wonder. As we keep peeling the cosmic onion, what incredible, reality-bending structure are we going to discover next? Thank you for exploring this with us today. Keep questioning, and we'll catch you next time.